Well, I think we'll get started now. Welcome, everyone. My name is Shelby Arendt, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with John Perkins and Jamie Kostelnik. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with your microphone and video. We will wait to the end of the presentation to take questions. And in the meantime, please do your best to make sure your microphone is muted when you are intending to speak. It is my pleasure to introduce Guo Yu, who is an assistant research professor at the Desert Research Institute, as well as a licensed professional engineer in the state of Nevada. Dr. Yu has a PhD in civil and environmental engineering from the University of Wisconsin-Madison, and he studies weather and climate extremes using both statistical and physics-based modeling. He moved to Reno, Nevada last December with his wife and their 3-year-old twins, and he says he's enjoying life at the biggest little research institute. So today we're going to hear about some of his work on post-wildfire hydrologic response and how this can affect floods and debris flows. So with that, you can take it away, Guo.
All right, thank you, Shelby, for the introduction, and thanks for the John Perkins for the invitation. Even though my work is now like 100% related to the landslide hazard, but I'm very interested in collaborating with people in that direction. Hopefully we can get some context after the presentation. So before I start, I really want to thank a lot of people. Some of them are now shown, their name are now shown here on the front page, but especially for Luke Miguel, Brian Ebel, and Trevor. So they are the main collaborator for this study and also some of the future works. And I call it wildfire continuum flood frequency analysis. So you can think about that as two parts, the flood frequency analysis. I will spend a little bit, I think, more time, like give you a very hopefully detailed background on the flood frequency analysis, or FFA, and then how does that connect with the wildfire. So to start, I want to say, like in a big picture, what I do through my PhD until now is on the risk assessment, because those extreme weather and climate events rarely happen. So, and also it has huge uncertainties for understanding them. So using the risk assessment is one approach to quantify the probability of those extreme events. So for flood frequency analysis, FFA, so it is basically the relationship between flood magnitude and is also associated probability of happening. So it is critical in civil and environmental engineering for a couple of reasons. And also it has been widely used in the hydrological practices. For instance, we use that information for flood mapping, and we use that for design infrastructure. And also, if the estimate is wrong, it can cause a huge impact. So flood frequency analysis, the output from the flood frequency analysis is something you see here. It's called a flood frequency curve. So it shows you on the y-axis is the flood magnitude, so how big the flood is, and on the x-axis is the annual exceedance probability. In other words, reoccurrence intervals, or we call it return periods. So some like the term you heard from news or newspapers, like the 100-year flood. So that represents in any given year the probability of occurrence of river exceed that magnitude is 0.01. And also the flood frequency curve, it ranges from more frequent events to the upper level, which is the rare event, but once it happens, it can cause a huge impacts. And for different hydrological practices, they use the different range of these flood frequency curves. So for instance, the FEMA flood map is focused on the 100-year events, while the stormwater management, they focus on the more frequent light severe event. like for instance, like a 20-year or 10-year. While for the dam safety, they are more, or sometimes like the nuclear power plant for the flood risk analysis for those critical infrastructure. They focus on sometimes even larger than 1,000 or 10,000 year events. So they rarely happen, but once it happens, it can cause a huge impact. So we call that upper tail. So upper tail flood frequency, so which represents high severity but low probability. So the main purpose of doing research on flood frequencies is try to improve the robustness of the FFA. So to do that, the main idea behind that is to enlarge the sample size, because we have really limited data, but we try to understand the floods rarely happen. So for instance, for most of USGS gauges across the US, we have less than 100 years annual peak flow, but we try to estimate 1,000-year or even reoccurrence interval longer than that. So the key idea is to how can we enlarge the sample size. So there are three principles. The first one is called extending time. So what does that mean is try to use the paleo flood analysis. I know there are a bunch of people from USGS are working on this direction. So they can by looking at those like a geomorphology of the river networks and try to find those like a ancient flood record. And then by using the dating technology, you know what is how many years ago does that event happen. So that information can help you to understand the robustness of your flood frequency analysis for those rare events, like let's say 100-year or 200-year events. The second principle is called trading space for time. Because when you look at one single watershed or gauges, you have limited sample size. But by expanding your study area to a regional, you can leverage the data from nearby region. But sometimes we have to be careful. You have to delineate. We call it hydrometeorological homogeneous region. So which means the watershed properties are similar to each other. The rainfall and runoff properties are similar. So which means you can leverage the data from the nearby region. So in the regional flood frequency analysis technique, they call it index flood method. So which you use USGS gauges from a regional rather than a single watershed. And also a part of my PhD work involves in the stochastic storm transposition. So which is based on the rainfall rather than the look at the stream flow data directly. But the idea is similar. It's like rather than, because the rainfall is the most dominant drivers for flooding, but by looking at rather than just where rainfall happened within your watershed in history, you can look at rainfall happening in a nearby region within a hydrometeorological homogeneous region. By randomly resampling and transposing the rainfall within that region, some of the rainfall could provide more information on what is a possible rainfall scenario for the watershed of your interest. And the last one, we call it process-based understanding. So that is mainly what I will talk about today. So the idea is we are now looking at the flood flows directly. We look at what is the drivers of the flooding, and then we try to understand what is a combination of those drivers causes flood, and by mimic that processes to generate the model simulated flood, and then that can also improve our sample size, although they are model sample size, but still can help us to understand the robustness of the flood frequency, especially for the upper tail. So here's the framework of the process-based flood frequency analysis approaches. It's different from the statistical modeling. the main idea is we still have to start with the historical flood observation, but this time we didn't directly use that observation to fit a statistical distribution. Instead, we try to understand what causes those historical flood peaks. So by doing that, we have to decompose the flood peaks into their drivers. So from the technical perspective, you always need to leverage modeling to do that part, because otherwise it's hard to decompose your peak flows into different flood drivers. And once you have those flood drivers, you understand their marginal distribution and also correlation. You can fit them into a Monte Carlo simulation. So which means you randomly sample those drivers and you can simulate a peak flow, assuming you repeat the whole processes a lot of times. And then you can have a variety of annual peak flows, simulated annual peak flows. And then their empirical distribution is what we call here. All those blue dots are simulate events from those Monte Carlo simulation. So their empirical distribution is what we call process-based flood frequency analysis. It's different from those right line, which is the fitted statistical distribution curves. Since I'm in Reno, I'm gonna present this framework in a Nevada style. So here you go. I think for people who is new to this field, to this idea, you can think about what I just described as a slot machine. So we're trying to understand the probability of flooding, but here you see we are not directly use the flood peaks. We use their drivers of that flooding. So for instance, for this case, you have a moderate rainfall, a little bit snowpack, wet soil moisture, and moderate like a reservoir level, a water level. And you use all those drivers, put into your hydrologic model, you simulate a peak flow. And then you run your slot machine for another combination of flood drivers. So this time you have an AR, atmospheric river happen with snowpack, so rain on snow events, but then you have a very dry soil and also very low water level, and you simulate another flood peaks. If you play this slot machine again and again, you can get a lot of like a simulated annual peak flows, and then their empirical distribution is the process-based flood frequency analysis. So which means you can estimate the probability of those rare flood events. I will go through one example with you. I know most of the people in this group, in this audience, are from Colorado. So actually, the Bureau of Reclamation, who was the funding agency for my PhD work, and by working with the reclamation, we use this Big Thompson River watershed as a case study. So we only look at the upstream of the Big Thompson River, which is the outlet ends as a Lake Estes. So it's a relatively small watershed, around 357 square kilometers. And as you can see from the land use type, it is mostly forest, and only as a close to the watershed outlet, you have some like urban area. And we use that, and also for some of you know, in 2013, September 2013, it occurs like really severe flooding in this watershed. And that was happening in a very rare season, because most of the flood season for this watershed is snow melt driven, happening in April, May, and June. But this one happening in a very late summer, and it is mainly rainfall. But it causes really huge flood events. So here you can see the magnitude is around 84 cubic meter per second. And here I show you the conventional approach for flood frequency analysis. So you collect the observe the stream flow. Mostly we use USGS, observe annual peak flows, and then you fit into a statistical distribution. Here I use the log Pearson's 3 distribution, and then I show you the 90% confidence interval. As you can see here, by using the conventional approach, the 2013 September flood looks like an outlier because it's even above the 90% confidence interval of the fitted statistical distribution. And this is my process-based simulation. So here I simulated 10,000 synthetic years. So for each year, I have different flood drivers. And then by running those flood drivers into a hydrologic model, I use warp hydro here, and then you can simulate annual peak flows. I repeat the process 10,000 times for 10,000 synthetic years, and then their empirical distribution. So here it shows you the plotting position of these simulated 10,000 peak flows. So that is the process-based flood frequency curves. As you can see here, as a more frequent events, my simulated curves is on the lower bound of the statistical distribution, while as it's moving towards the upper tail, it become higher than the upper level of the 90% confidence interval. The main reason is that my simulated, so the main reason is there's a mixed flood generation happen here. For more common events, they are snow melt, but for the very rare events, they are rainfall driven. But my process-based flood frequency curves capture those dynamic changes in flood generating mechanism with respect to different spectrum of the flood frequency curves. And you can see here, if we try to estimate what is the recurrence interval for the 2013 September flood event, it was around like a 200 event based on my process-based approach, but it can be 2,000 year event based on the conventional statistical distribution. So a huge difference. But what I'm trying to share with people is, imagine I share these estimates with the stakeholders from the Big Thompson River, and then they ask me, hey, Guo, how robust is your estimate for 10,000 year events? So from the statistical distribution, I mean, I can talk about scale parameter, shape parameter, etc., but I really cannot answer this question using my hydrology knowledge. But for the process-based flood frequency analysis, I think I can start a conversation with the stakeholders because I can show them, hey, I've shown you what is happened behind these largest simulated peak flows, this 10,000 year flow. So this is based on average, some K forcings and response variables along the watershed. I can show them, hey, you see that's a rain on snow events, the precipitation rate, and also the snow melt rate along those like a 3 or 5 days period. And you can see it's really warm and cause a huge negative sensible heat, which means the ground is absorbing the energy from the above air, and that causes ground temperature increase way above the freezing level and causes snow melt, and the sway is decreasing along the period. And then I can show them the topsoil moisture and deep layer soil moisture. So here, because it's the forest land type, the infiltration capacity is very high. So that's why you see a huge increase in the deep layer soil moisture along the event. And finally, the peak flow step reaches like 2 steps until those like above 150 cubic meter per second. So that's how we start analyzing what is 10,000 year event look like with the stakeholders. So that also gives the opportunity for those stakeholders to get involved in deriving the flood frequency analysis. I think that's a interest me because they have the more local expertise. They probably can tell you, hey, Guo, the rainfall rate for that amount is probably too low, and then we can start conversation and to see how can we adjust some of those drivers to improve the robustness of the estimates. So I show you one last thing about those Big Thompson River watershed. So here is also the peak flows I show you two main flood drivers. On the X is the 72-hour precipitation, so total precipitation. On the Y-axis is 72-hour snow melt. So that's the main two flood drivers for this watershed. And then the color represents the peak flows. All those points here are from observation. So that's a historical event. As you can see here, as the bones driver is at very low value, the peak flow is also low. But as you move towards like a more rainfall or more snow melt, you see in general the peak flow, the color becomes more yellow and green. So which means the peak flow gets higher. And that's a very extreme event. That's the 2013 September event. There's no snow melt at all because that's the dry season in this watershed, but a huge amount of precipitation that still can cause very high peak flow. So that's our understanding from the observation. And then here's the understanding we can get through the Monte Carlo simulation. So all those like small dots, that's my simulated peak flows. But you see my model, my framework capture the general term. So as the snow melt and precipitation are smaller, you have very blue and green color of the dots, which means small peak flow. And then as you either moving in the like a higher snow melt and higher precipitation, the color becomes yellow and red, so which means you have a higher peak flow. And also my model captured those like a very rare, like a rainfall driven flood events. For instance, the largest the simulated peak flow you see here, we have like a zero snow melt, but still very large annual peak flows. So I think that's at least the direction I want to work on in the future, because it at least try to get the correct answer for the right reason, right? And also I'm very interested in those like a simulated events. I call them, are they just not yet observed? So which means they have a probability to occur, but from our limited historical observation, we haven't seen them yet. Okay, so I spent a lot of time on the background on the flood frequency analysis, process-based flood frequency analysis, and also how I technically develop those framework for simulating the flood frequency. And then once I moved from Wisconsin to Reno, everyone is talking about wildfire. And then I was thinking, how can I incorporate the wildfire into my flood frequency analysis frameworks? Because if you ignore the wildfire in the watershed, which is wildfire-prone region, you just place like a zero probability of those wildfire. But we do know that happens, and we also do know once that happens, it may enhance our flood peaks. So this is if you haven't read this paper, please do. This is a great paper from my collaborator, Luc Beguier, on the Nature Review, on how the wildfire process occurred from hill slope to the downstream at a watershed level. So my key takeaway from this page is like, especially for the moderate to high burn severity wildfire occurred in the headwater basin, hill slope scale, it may cause hydrophobicity and then debris flow. So eventually those reduce the infiltration capacity and enhanced runoff efficiency will reflected on the downstream stream flow or peak flows. So to answer this question, how to incorporate wildfire into the flood frequency analysis, we start with where is a medium-sized watershed, Arroyo Seco watershed in Southern California. The reason why we choose this watershed, a main reason is it has a lot of like data available. So it has USGS gauge the stream flow for bones pre-fire and post-fire condition, and also even after I think 10 or 12 years after the 2009, station fire. It still have the gauge, and also it has like a rain gauges at 15 minutes intervals for a longer time period. The data availability is one of our criteria for choosing those case study watershed. And in the middle, the map shows you the 2009 station fire burn severity map. So you can assume moderate to high burn severity occurred across the entire watershed. And on the right-hand side, I show you the annual peak flows from USGS for over 80 years. For over more than 100 years for this watershed. And I plotted them as using the empirical distribution. O is plotting position. So along the X, that's a recurrence interval. On the Y is a peak flow. So I want to play a game with everyone here. So I give you 5 seconds to guess which points here represents the peak flows right after the 2009 station fire. So let's say 5 years after the 2009 station fire, which points here are the peak flow? All right.
Maybe folks can throw their. Oh, you gave it away. I was gonna say guess.
All right, I screwed up. I showed the answer already. Okay, so I don't know if it surprised you or not, but it did surprise me because everyone's talking about post-fire flooding. It's a severe hazard, but you see the first year right after fire, it's not the record flood. It's not even the top 5. So the one thing I want to emphasize is never forget the other flood drivers. So which means even you have a severely burned watershed, it doesn't mean the rainfall right after the fire can also be severe. Maybe you just have moderate rainfall after that. And the other thing interesting is I have to say the rainfall intensity for those 4 annual peak flows are different, but you see to some extent the recurrence interval drops from like around 20 years to less than 1 year, so 4 years after the fire. So it somehow shows you the watershed recovery, the watershed properties recovered to the pre-fire condition to some extent. And also, when I say wildfire impacts on the flood frequency analysis, it's not how the peak flows changes right after fire. It is what I'm trying to understand in how the shape of the flood frequency curve will change. Are they moving towards the same direction across the recurrence interval, or not? No, sometimes enhanced, some reduced. So that's the question. That's what I see wildfire-affected flood frequency analysis. Okay, for that reason, as a group, we thought the conventional statistical modeling approaches are not appropriate for 2 reasons. So the first one, as we have seen already, the post-fire and pre-fire flood generating mechanism are different because the impacts of the burn severity on the soil property. So which means we cannot group those peak flows into one group and fit a statistical distribution, because otherwise it violates the IID assumption. So the samples has to be identically and independently distributed, right? Then which means you have to separate them together. And then that comes to the second challenge. We have very limited post-fire flood samples. So for two reasons. One, even for the most wildfire-prone regions, the wildfire burn occurs on a time interval probably longer than 20 years or 30 years, but our flood records are limited most of the time. And also because of watershed recovery, after few years, the watershed, the flood records does not represent the post-fire condition, right? So which means you have very limited post-fire flood records, which means is too limited to fit its own statistical distribution. So for instance, here, I'm not brave enough to fit only 4 peak flows to estimate 500-year flood. Okay, for that reason, I think that can be like a smooth transition to incorporating wildfire and also the flood frequency analysis by using the process-based approach. So it is still like what I just showed you earlier by understanding those drivers, by using the model simulation to simulate those synthetic peak flows. So here's the very simple proof of concept study we perform. So very simple. We just assume like a pre-fire condition, just like 2 drivers, rainfall and initial soil moisture. So we use the rainfall weather generator to simulate rainfall time series at 15 minutes interval because the post-fire flooding are very dependent on those short-term, short duration, high intensity rainfall. And to incorporate the wildfire into this framework for this very simple analysis, we thought there's 2 ingredients are missing here. The first one is in my 500 synthetic year, how often wildfire will occur. And the second ingredient is once it occurs, what is the hydrological impacts? In other words, how should we perturb our hydrological parameter to reflect such an impact and also the recovery of the watershed condition. So just 4 drivers for this simple study. And then we can simulate those 500 synthetic years. And then the simulated results of those like 500 synthetic annual peak flows, their empirical distribution is the flood frequency analysis accounts for the wildfire. So to understand the wildfire impacts on the flood frequency, it's not just the post-fire period. You have to think about this as a continuum. So finally, that comes to my presentation title, Wildfire Continuum Flood Frequency Analysis. You remember I mentioned even right after the fire, other flood drivers may not be that severe, or sometimes it is. Really, you have to understand the interactions of all the different combination of those flood drivers, how they interact with each other to shape the changes in the flood frequency curve. So I call it flood continuum because we try to mimic the range of possible flood responses to the continuum of watershed conditions from pre-fire to abrupt perturbation due to fire and then to the post-fire recovery. Okay, so that's the concept. And to answer the first question, how often wildfire will occur, we leverage the U.S. Forest Service simulated annual burn probability. So I can give you some like a brief overview of what they did. It's also they simulate, I think, a mailing wildfire season with different field conditions, climate conditions, lightning, and human-made fire ignition. And then they use the model combination called FSA, so FSIM and flap map to simulate the wildfire ignition and spread. And then they repeat the whole process mailing time. And then they calculate how many years wildfire occurred divided by the mailing year, and then to get those probability map. So they have done that for different wildfire severity. So for this study, I only focused on the moderate to high wildfire. So as you can see here, that's their simulated probability. And on the left-hand side, that's the MTBS, so satellite derived wildfire parameters from 1984 to 2020. So 40 years wildfire parameter. So what I want to show you is that, as you can see here, for the region where the simulated probability is very low, you're also seeing less frequent wildfire occur in that region. But for those like a purple region, you see the simulated probability is high, which is also corresponding to those very frequent fire observation derived by the satellites. So what I'm trying to say is the model did a decent job for simulating the fire probability. So in terms of my Arroyo Seco watershed, so the probability is around 0.008, so which means in average around 116 years, a moderate to high burn severity fire will occur on this watershed. But that's just a deterministic single value. It doesn't provide you any uncertainty. But when the U.S. Forest Service did this simulation, they focused on the South Coast ecoregion, where they assume the land type, the field type are similar to each other, the climate are similar to each other, so which is kind of like homogeneous. So then I did a space for like a spatial bootstrapping. I randomly assumingly move my watershed within the region. The idea is to get uncertainty of those wildfire occurrence. So that answers the first question, how often wildfire occur. So in my 500 synthetic simulation, I just sampling from this box plot. And once that wildfire occurred, that came to the second question, how should I perturb the wildfire hydrological impacts? So for this study, I just talked with Shelby at the beginning of the presentation. It's also kind of our limitation. So it's not purely physics-based understanding. We leverage the data and perform kind of like an empirical-based analysis by using the inverse modeling. So which means, so the first row here is a model performance KGE value. Higher value means better performance. So to make our model to achieve a higher KGE value for those post-fire period, we really need to decrease the KSAT, the saturated hydraulic conductivity and channel roughness, to achieve a relative good KGE. And then as the time moves on, we have to make the value, we have to increase the value a little bit to achieve a relative good KGE value. So that's our wildfire impacts on the hydrology in this study. And then we fit a logistical regression to those box plot, because by fitting a logistical regression, we can make a connection between wildfire impacts with respect to time since fire, right? Remember, in my first question, we kind of figure out how often wildfire occur. Once that occurs, I dynamically change my model parameters and then let it evolve back by following this logistic regression until the next fire, and then I perturb my parameters and let it evolve back. By doing that with 500 synthetic years, and then I play this game like 100 realizations. So finally, we get our flood frequency analysis accounts for the wildfire. So to be honest, when the first time when we saw this, my group and I, we were discussing, did we do something wrong? Because everyone is talking about wildfire impacts on flooding. We are supposing to see an enhancement across the reoccurrence interval. But we do see that they are similar to each other, but only difference is more on the upper tail, but also a huge, the standard deviation has become increased as a upper tail. So we finally figured out the part of the reason is this watershed, the recovery is very quick, at least in terms of those like soil properties. A quick wildfire recovery, and also the longer wildfire reoccurrence interval causes those like the flood frequency are similar for those like more frequent event. But for testing, is there anything wrong with our model? We focused on those flood frequency curves that accounted for wildfire, but we separate them into two groups because all the colors here represent simulated events. We know what happened for each of the events. So we separate them into two groups. So the first one is 4 years after the wildfire, where their peak flows, we group them in one group. So it is like 5% of them. And the other 95% of those simulated annual peak flows occurred like out of this window, so longer than 4 years after fire. So we separate them into two groups. Now we have even the post-fire period. We have like a 2,000 peak flows. It's still like a more sample size than the observation-based analysis. So we did a simple bootstrapping. We randomly select 100 peaks from each group and plot their plotting position. And then we repeat the processes another 100 times. So we got those different plotting position. So you can see here for the group 4 year, within 4 years right after the fire, we do see enhancement across the recurrence interval. But for those after longer than 4 years, due to the rapid wildfire recovery, their bootstrapped plotting position are very similar to the pre-fire USGS observed plotting position. So which means this is what we call conditional flood frequency analysis, right? Because we condition on the post-fire period. But this red curve here is an unconditional one because that accounts for the probability of wildfire occurrence. So to sum it up, we define a wildfire continuum flood frequency analysis, and the result shows a large variability than pre-fire, especially for the upper tail. And the results highlights the importance of wildfire inter-arrival time and post-fire recovery process on driving the changes in the flood frequency analysis. And so recently, our group, so Luke, Brian, Trevor, and I, we received funding from USGS to continue to work on this project for the next 3 years, but we try to expand our study area for 5 fire-prone regions in the western US, try to understand what is the interaction of different flood drivers and wildfire, different field type, how do they affect the regional flood frequency analysis. And also for those of you who are interested in collaborating with us, feel free to reach out after the presentation. I think I finished on time. Is that correct, Shelby?
Yes, that was perfect. Well, we have
Nice.
we have plenty of time for questions.